Hey, Zamfam. This is Mr. Kennedy talking about gravity. Yes. A wonderful, universal, huge idea of the universe to distract you from what's going on right now. Gravity. Good old Sir Isaac Newton. Not only did he have three very important laws, he also had something to say about gravity. He hypothesized, because he never could really prove it experimentally. He had to wait for this English guy, Cavendish, to prove it with data. But he hypothesized that anything with mass will attract anything else with mass. So, for instance, this is my daughter's fancy rock. She loves to collect rocks. This is a Sharpie. All right, these two things have mass. Yes, they have stuff, little particles. They have matter. So there is, by just the way the universe sort of unfolded, an attractive force between objects with mass. Now, it doesn't really feel like that right now. They're not getting pulled together like a magnet. He said that this relationship was based on both the object's masses and the distance they are apart. Further away, less force, more massive, bigger force. All right, so there's this sort of mathematical relationship, and amazingly, a fellow about 200 years later proved it and came up with a number, which we'll talk about. So the big idea is that when we talk about small objects, yeah, we can't really measure or see the attractive force, but when we talk about big objects, like I'm talking really big, like the moon, the earth, Saturn, Venus, Mars, the sun, galaxies, when we're talking about those types of objects, those are probably things where we're going to see the effects of that gravitational force. So, little review and some equations, a little bit of math, and we should be good to go to complete this last worksheet on this unit of central net force. So I'm going to turn us over to our American Girl doll stand. All right, might have to do some adjustments here. Old school way of figuring out gravity was pretty nice and easy. On planet Earth, we just take the object's mass, we multiply it by g, which on planet Earth is 9.8 or 10, and we get our force of gravity. Now that's all fine and dandy when we're on planet Earth, actually on the surface of planet Earth. So if we go up to the top of Mount Everest, this might not work. If we go to the depths of the ocean, this might not work. If we dig a huge hole halfway to the center of the Earth, this might not work. If we launch a satellite up, 100 kilometers, so that it orbits the Earth, this might not work. But good old Newton's universal, it's in the name. Universal means you can use it anywhere in the universe. If we go outside the universe, multiverse, it might not work. That would be bad. New Newton to figure out the multiverse law of gravity. So what he claimed, and he wasn't even able to figure that out, this is the stuff that he said, hey, this is what matters. The mass of the two objects and the distance between them. That's all these little letters represent. M1 represents the mass. Let's say the mass of the, where did the rock go? The rock. And the mass of the pen. Where'd the pen go? The pen's right there. And then the distance between them, all right, 10 centimeters. We could figure out the attractive force. It's probably going to be really, 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 really small just by using this equation. But you say, hey, Mr. Kennedy, what's that big old G there? Yep, that's the big old G. That's the value that good old Cavendish figured out using just metal spheres and a bit of twine, a little wire. But you can look that up if you're really interested. So what we actually want to do is eventually compare these two things and see if we get the same G values, that 9.8 that we experimentally got in our labs, using this equation, knowing some values. But conceptually, the important part is that we're going to move from a more specific definition of gravitational force to a more general universal. It actually takes two to, not tango, that's a dance if you don't know. It takes two to gravity. Without the Earth, we would have no gravitational force pulling on us. Without the moon wouldn't cause tides, wouldn't pull at us. Gravitational, just like Newton's third law, is a two-way street. For every force, there's an equal and opposite force. The Earth is actually pulling on me with a force of gravity, but I'm actually pulling equal and opposite on the Earth. Now, the Earth is really big, so it doesn't really care that I'm pulling on it. But I'm really small compared to the Earth, so I feel that. Still can't dunk a basketball someday. Now, so this G number is 6.67 times 10 to the negative 11th. What does that mean for all you math scholars? Good old scientific notation. We're going to start to use that. It is your friend. Don't be afraid. Please don't be afraid. Negative 10 just means we're going to move the decimal place 11 places. Now it's negative, so it's going to think it's going to be bigger or smaller. You guys are so smart. Smaller. We're going to move this sucker 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's the number. If we want to write it out here, let's see if I did this right. 6.67, I move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Big pain to write these numbers out because they're super, super small and a waste of ink. So we're probably not going to write these out when we solve problems. We're going to leave it in scientific notation because we're math scholars and we'll be able to work with this number so much more efficiently and quickly and easily. All right, so G is just a number for our universe. M is the mass of whatever object we're talking about. M2 is the mass of the other object. So we could be talking about the sun and the earth. We could be talking about the moon and the earth. We could talk about a satellite on the earth. We can talk about me or us, a person and the earth, or a person standing on the moon. Now, R is the distance between the centers of the objects. So if we're especially talking about the earth, we're going to measure the distance from the center of the earth to the surface of the earth, the radius essentially of the earth. That would be the distance. It's not the distance from the surfaces of the objects, it's from the center of, technically the center of mass of the objects, but we don't have to worry about that. All right, so now for calculating little g. So let's say you are standing on the surface of the earth. I know, you're sort of big here. Not drawn to scale, I apologize. That's you. Green, spherish-like thing is the earth. We have two givens here. We're going to give you the mass of the earth. 5.8 times 10 to the 24th. That should be kilograms. Oops. I'll write that in a second. And then the radius of the earth, 6.38 times 10 to the 6 meters. Ooh, two naked numbers. I apologize. I will cover them up really quickly. So the old way to figure out the force of gravity is just take the mass of the girl, maybe she's 50 kilograms, multiply it by 10 or 9.8, and we get the force of gravity acting on the girl. The new way, the universal way, that's going to work both on Earth, but it's going to work like if you're floating above Earth, it's going to work on Saturn, Mars, Neptune, all those places, is to take that nasty number G, mass of the girl, mass of the earth, and the distance between the two. Now, when we say things are standing on a surface of the earth, the R value, we're not going to worry about like the center of the person because that's relative to the size of the earth. It's really small. Let's say, she's 2 meters tall to make it easier. We'd add an extra meter, but that's so insignificant, especially if we're talking about sig figs. Now, if we have a satellite floating up there, 100 kilometers above the Earth, which you might have in the homework, yes, we would worry about that. But because this person's on the surface, we just say radius of the Earth is what we're going to plug in there. We're going to say, okay, we could plug in the mass of the girl, we can plug in the mass of the Earth, we can plug in that nasty number G, and we could figure out the force of gravity acting on this girl. Well, actually, the only thing we don't have is the mass girl. I wonder if we need the mass of the girl to figure out if the G is the same. Ooh, these are two of the red equation, the blue equation are calculating the same thing, right? So let's take this down for a sec, and let's say M of the girl times G is equal to, I'm over here, big G, M of the girl, M of Earth divided by the distance between them squared. All right, let's see if this works. All right, so what I'm going to do now is just set those two equations equal to each other. Oh, hey, make my life easier a little bit. Mass of the girl is on both sides, so we're just going to get rid of that. Let me show you that. See how that works? Yeah, whatever it is, it's going to cancel mathematically. They're both sides of the equation. Let's plug in some numbers. G is what we want to figure out. And if it's pretty darn close to 10, then hey, you already calculated that experimentally. We got our big G, 6.67 times 10 to the negative 11th. Horrible number. We got, I'll change the colors up here. We got the mass of the Earth. That was given to us, 5.98. That reminds me to put some close on that number. Times 10 to the 24th kilograms. Close on that number. And close on the radius of the Earth too. And then we divide it by the radius of the Earth. Let's add some color here. Radius of the Earth is 6.38 times 10 to the 6 meters. But that is squared. So actually, the distance between stuff matters a whole lot more than the masses, because we got that squared relationship. All right, do we see what we did there? We canceled the mass of the girl, because that actually doesn't matter when we're calculating little g. And then we put in that nasty small number, 6.67 times 10 to the negative 11th. We're going to multiply that by the mass, and then we're going to divide it by the radius squared. Now those look like horrible numbers to multiply, Mr. Kennedy. Yes, they are. So here's the trick. With good old-fashioned scientific notation, the beauty of it is that you don't even worry about this 10 to the negative 10th, 10 to the 24th, 10 to the 6th, also squared just yet. Wait to the very end. And just multiply the numbers beforehand. This number, and then divide by this number squared. Make sure you square this number first. So that's what I'm going to do. I'm going to multiply this number times this number, press enter, and then divide it by 6.38 squared. Let's see what we get. I'm supposed to do it somewhere else. Did I do it somewhere else? This page fall down? Oh, it's over here. All right. So when I did that, I got my G, so 6.67 times 5.98 divided by 6.38 squared. Oh my gosh, no way. Sort of right, but might be wrong. So I got that number when I just multiplied the first part of the scientific notation, those numbers that are in between, 1 and less than 10. But I can't forget the good old base 10 powers here. But there are some rules you should have learned in algebra class by now, that when you have the same base exponents, you just add them. Negative 11 plus 24, what's that going to be? Negative 11 plus 24, that's just 10 to the 13th. Okay. So up top, we're going to say this is 10 to the 13th power. And then down below, ooh, there's another exponent rule you should have learned by now. When we take a power to a power, so we got 10 to the 6th squared. Ooh, shout it out, shout it out. What do you do to those powers? Yes, you multiply them. So this just becomes 10 to the 12th You are kidding me here. Oh, we are reviewing. I'm doing your math teacher's job. We are reviewing all sorts of exponent rules. Then we have this number. That's just a number. Then we have 10 to the 13th. So 10 times 10 times 10 times 10 times 10, 13 times. And 10 to the 12th. 10 times 10 times 10 times 10, 12 times. But you know those exponent rules. Same base exponents, and you're dividing. Oh, yes, you know. Shut up. Yes, you subtract. 13 minus 12 is just 1. So it's just 10 to the first. Or, are you kidding me? Just multiply that by 10. What do we get? We get pretty darn close to 9.8 if we're looking for sig figs. Well, we just proved that the gravitational field constant on planet Earth using Newton's universal law of gravitation is 9.8. Well done. I'm even going to put in a unit there because that's a naked number. It's either meters per second squared, or we could even say newtons per kilogram. Bravo, people. Well done. All right. Have a wonderful break. Bye.